Okay, so hello everyone. Welcome to BC session number 3. So let us recap what we have done last time. Last time we have seen two JFET DC biasing circuits. One was cell biasing, other was voltage divider biasing. So this was one of the circuit. So for this circuit, they have given JFET parameters, IDSS and VP, and we were supposed to find a Q point and a VDS voltage. Okay. So we did some mathematical analysis with using the formulas, and we got the value of VGS, ID, and VDS. Okay. Similarly, we did the analysis for a voltage divider bias circuit, which is shown over here. Again, this also had a JFET parameters being given, all the resistors parameters being given, and you are supposed to find the Q point and the VDS value for the circuit. So we did some mathematical analysis with the form of equations, and we got the value of VGS and ID and VDS. So what do the values mean? So see, Q point means that it will determine the current. It will set the current and the particular voltage, that is IDQ or VGSQ, or we can say VDSQ or IDQ. Okay, such that your transistor works in the saturation region. So over here, I have just plotted. We have just seen this before. The Q point is on the on the transfer curve, and the yellow color line is my DC load line. Similarly, we have seen this technique. We have already discussed it in detail. The yellow region over here, shown over here, is the saturation region. So our objective of biasing is to establish a Q point so that the JFET wakes up. Okay, so the JFET wakes up and start working and start to work in the saturation region. So that was the objective, and we started our session like this. The transfer characteristics and the output characteristics are closely related. The transfer curve is derived from the output characteristics. So whatever DC load line we draw for the output characteristics, similarly we draw the same for the transfer characteristics. Okay, now let us begin with today's topic. So this is basic electronic circuits session number 3. So let us begin. So the first point is amplifier requirements. Now, what do you understand by amplifier? Okay, an amplifier is something which will have an input, which will have an output. So what are the requirements? I've written down the requirements as gain, input impedance, output impedance, linearity. What do they mean? Okay, now instead of asking you all, I will inform you all directly that amplifier always may not be a voltage amplifier. In your curriculum, you all are studying voltage amplifier, no doubt, because amplifier is one variety of amplifier. You all can have various types. So in a voltage amplifier, your input is a voltage. So we normally call it Vin. I think in all the circuits which you are studying, you are using voltage amplifier, correct? And your output is your voltage. Fine. So in this curriculum which you are studying mostly voltage amplifier. But for your information, there are different amplifiers where the input can be a current, output can be a current or a voltage. There are only 4 types of amplifiers: current amplifier, voltage amplifier, transconductance amplifier, and transresistance amplifier. Now, since we are focusing only on the voltage amplifier, we will define the following for the amplifier requirement. So what should be the gain? Now, whenever we say gain over here, we are referring to voltage gain. Okay, we are referring to voltage gain. So obviously, if it is an amplifier, your voltage gain, which is represented mostly by AV, should be very high. Okay, then only it will make sense, right? Because a small signal at the input, you are going to amplify at the output, correct? So let's say this is my small time varying signal, okay, and you want to amplify it. So this will be my output. So you're amplifying with a voltage gain. So your voltage gain should be very, very high. What about the input impedance? Well, I am not discussing in detail what is input impedance. That I may discuss when I discuss the problem. The input impedance is represented by Zi. Many textbooks call it as Zn or also Rin or Ri. Okay, this input impedance also should be very, very high for a voltage amplifier, and this is done to avoid the loading effect on the source. Okay, now output impedance of a voltage amplifier should be low. It is denoted by ZO, and it should be low. This is specifically for voltage amplifier. And what do you mean by linearity? What do you mean by linearity? Linearity means the output which I get, output at which I get at the output of an amplifier should be linear with respect to input. This is extremely important. What will happen if your amplifier is not linear? You're giving a sine wave, a small sine wave at the input, but at the output you may not get the same wave shape. You are expected to get the sine wave, amplified sine wave at the output, correct? So if your amplifier is not linear, what will happen? Your wave shape nature, input will be a small sinusoid, output may not be a sinusoid, irrespective whether it is a whether it's amplifying or not. Okay, so that is the reason why your output should be linear with respect to input. Fine. Now there are some facts which I am discussing now. So the first fact is JFET as a device amplifies small time varying signal. Now the next few minutes we are going to see why is this. So for a time varying, small time varying signal, your sine wave is a time varying signal, but it may not be small. So we will study what do you mean by this small. Okay, what do you mean by this word small? So, but this requires your JFET amplifier to be linear. Okay, this requires your JFET amplifier to be linear. You know what are the four properties? The four properties, linearity, and that is very, very important. Now, also there is one more fact coming up. Fact means it's been proven. JFET is a voltage dependent current source. JFET is a voltage dependent current source. So that means it converts a voltage to a current. And remember, we have seen the equation ID is equal to, we have seen this equation, ID is equal to IDSS into 1 minus VGS upon VP. Now, in this equation, how many parameters are constant? So, among this, the parameters which are constant are IDSS and VP. So, basically, we are relating ID and VGS. Now, what is ID? ID is the output current. And what is VGS? VGS is the input voltage. Hence, we say JFET is a voltage dependent current source. Okay, it converts a voltage at the input to a current at the output. Now, whenever we write capital VGS and capital ID, that is a DC quantity. And whenever we write a small VGS and a small ID, that is a AC quantity. Okay. So, any doubts so far? Anyone? Or shall I proceed ahead? Everything okay? Everything going fine?
Yes, sir.
Okay, fine. So, okay, fine. Let me know if I'm too fast. I'm going a little slow because this is very important concept. Next, third thing what we will do is we will superimpose DC with a small signal AC. Remember, JFET as a device amplifies a small signal time varying quantity. So we have to define how small should be the AC signal. So that is the goal of your JFET amplifier. For a JFET amplifier to work, you should superimpose your DC with a small signal AC. Now, don't worry about this external supply. This is a weird looking circuit. Do not worry about it. We have already studied the biasing circuits. So, what is the role of biasing, JFET biasing circuits? JFET biasing will wake up the JFET and allow it to operate in the proper mode, that is saturation. so that it works as an amplifier. Okay, so here what we are considering is, have you, I mean, here I am speaking to you with the help of earphone, or inside it we have a microphone. Okay, so let's say we have a small mic which is superimposed with the VGG voltage. Why you require VGG voltage? To operate the JFET in the proper region, that is saturation region. So this mic can act as a small time varying AC signal. Okay, so let us say it this way. So V mic is given by Vm sine omega t, and we know Vm sine omega t means what? It's a sinusoidal signal with the angular frequency of omega and with a peak to peak amplitude of Vm and minus Vm. Fine. So it's a sinusoidal signal. Basically, your microphone signal might be close to this, but it's this Vm and minus Vm will be very small, maybe 10 milliseconds peak to peak or 20 milliseconds peak to peak. Okay, so that's why we are calling it a small time varying AC. So what we do over here is we apply a voltage at the top, VDD. So here this resistor is the external resistor, which we call it as RD. So what will happen due to this? The current ID will flow. Okay, the current ID will flow, which will establish output voltage VDS. Fine. So why are we doing this? We are superimposing a AC signal along with DC. Why we want that? See, we require a DC biasing so that the JFET operates with a proper 2-point value. And why we require AC? Because we want to amplify AC, right? As simple as that. And that is where V out. So V out is taken from the drain terminal. Now listen very carefully. We have studied the transfer curve. Now what are we doing is we are going to combine your transfer curve and the time response. Okay, so look at the circuit now. It is fitting this. Okay, so if you see carefully over here, we have IDSS. This is the plot of ID versus VGS. Okay, I forgot to write over there ID. This is a plot of ID versus VGS, transfer characteristics. And we are superimposing the mic signal over here, the time varying mic signal. Okay, so what do we do is the highest point of the ID is the IDSS, and over here the most negative point of VGS is VP. We know what is IDSS is the drain to source saturation current, and what is VP? It's the pinch off voltage. Okay, so at VGS equal to 0, your device is already working with a maximum current, and when VGS is equal to minus VP, your device is off. Fine. And we have done a numerical wherein we have set a Q point. Correct? We have set a Q point at the center of the DC load line. So here also I can draw a DC load line. So listen carefully, what are we trying to do over here? What are we doing over here is, we have seen this mic signal, which is Vm sin omega t like this. Just we have to rotate 90 degrees. We have to rotate 90 degrees. And see, we don't only have a mic signal, we have a VGG also. So if I draw that, now concentrate on this. Can you see this curve? This is your curve for V in, basically. This is your DC plus AC. Okay, so this line over here, which you see the orange color curve, is my mic signal. And what is that line which you see over there? This is a VGSQ. Okay, so this line over here is the DC quantity. This is the DC value. So in this, let me mark, in this curve, this much is the DC. Okay, and this variation, the height of this orange color sinusoidal mic signal is my AC. So that's why I have combined AC plus DC. So this small AC signal is superimposed with the DC, and it is applied to the so what JFET will do. So we have defined, what we call it, a dark pink color line, which see is a what you call it as a it's a transfer curve. Now it's an exponential curve, right? It's a non-linear curve. But this non-linear curve may have a segment which is linear. Can you see this green color patch which I have drawn? So this segment is linear, na? Correct? So you can have, so even in an exponential curve, a small segment which can be approximated as a straight line. Okay. So what we do is we allow those small variations in the VGS. Now, what is VGS? VGS is nothing but your mic signal. So we allow the small variations in capital VGS. You remember in the last time we have found out capital VGS Q. So that capital VGS Q is this. So beyond that capital VGS Q, you are superimposing your AC signal. Okay. So iska jo, your middle part is, it's not zero. It's actually VGS Q. Fine. And we are superimposing AC means what? That AC mic signal will be varying over it. So let's say that this VGS Q is -2. So this variation will be, let's say, -2.01. Okay. And below it will be minus 1.99. That way the variation will be that way. So you're varying your capital VGS value by the amount of small variation. And similarly, if we extrapolate that point, we can see those variations in the ID also. So if I extend this point to the right hand side, we can see these variations, small variations in ID. We have determined IDQ before. Okay, we have determined IDQ before, but these variations, this red color curve which you see is the AC variations. Okay, so this will give you a clear picture. So this red color is my AC variation, and this IDQ is my DC value. You remember? Okay, so this height over here is my DC, and this height of this red color curve is my AC. So this is your AC, and that is what we are combining, AC with DC. So what are we trying to achieve over here? When we combine this transfer curve with the time response, we see that for a very small segment of this transfer curve, we have a straight line. So if we pass a AC signal, if we pass a small AC signal within the limits of this straight line, within the limits of this straight line, we can say that our amplifier might be a linear amplifier. So what will happen if I exceed this height? If I exceed this height, again it won't be a straight line. I cannot call it as a linear amplifier. Are you getting what I'm saying in this? Are you understanding this? Whatever I've described in the curve. So we calculate the Q point VGSQ. No doubt, we calculate the Q point VGSQ and IDQ, but we superimpose your AC signals, which are the small variations in the current and the gate to source voltage, which we are limiting ourselves to this straight line. The entire small signal model is based on this. Okay, so a big exponential curve, a small segment only can be a straight line, and the middle of it is the Q point. So you operate in this and you deviate slightly above or below it. That is what is going on in reality. Okay, remember, JFET is a non-linear device. Okay, and whenever we make an amplifier, we are attempting to make JFET as a linear device, and the attempt of that is to keep the signal, AC signal, very small. If you keep this AC signal in this limit, what will happen? Your amplifier will be a linear amplifier. Fine. I hope that this is clear. So why small signal? Why we call it small signal? So the idea here is to consider the small segment of the exponential curve to be linear. That's what we have done now. We have considered a small segment of an exponential curve to be linear over here. Okay. Now, the AC input should be small signal to be within this linear segment. I think we have discussed this point. Fine. Let's move on to the next. Any doubts over here in this curve, because we are moving ahead? Because we are going ahead in this. Any doubts over here, please? Anyone? You can ask now, or else I can proceed. Okay, no problem. So we'll go to the next part, building the small signal model. Next, we will build a small signal model. So the first part in this puzzle is GM. Now we have seen the GM before. So what is GM? GM is the slope of this, a small segment. Again, this is the transfer curve. A small segment can be approximated as a straight line. Can you see this black color line on that green color curve? This is a straight line. And the slope of that is your GM. So what is GM? GM is nothing but slope will be y2 minus y1 upon x2 minus x1. So it will be delta ID upon delta VGS at a VDS value of constant. So this unit of GM is a milliampere per volt, and GM is called as JFET's transconductance. Okay, so GM is given by delta ID upon delta VGS. And what is, we can rewrite this equation as follows. Delta ID is given by GM times delta VGS. So what is delta ID? Delta ID is small changes in ID. So that is represented by, this is represented by small ID, which is AC. So small changes in capital ID is your small ID. And GM represents the slope, which is a constant. You see, this black color line is almost like a straight line approximation of this exponential curve. That's why we are writing as a slope. Okay, we have a slope of a constant line, not of a exponential curve. Okay, but that in that case that will be called as a tangent. So this is the slope, which is a constant, and delta VGS is the small changes in VGS, which we denoted by a AC quantity, V small VGS. Okay, that's what I've written over here. Delta VGS means small variations in VGS, which is a time varying quantity. So this equation which we have written is very powerful. Delta ID is equal to GM times delta VGS. What this equation whispers to you? It whispers to you that the gate to source voltage controls the amount of drain current. Okay, so your gate to source voltage, which is at the input of the JFET, controls the amount of drain current. Fine. So we are attempting to make this non-linear JFET a linear element, and this is first step towards it. We are approximating this exponential curve to a small linear segment, and this is the effect of that. Okay. Now next thing is to derive GM. Now I hope that you all are having your notebook. So let us do that together. So let us start with this equation GM. So, okay. So this is, let's say, our first step. So we have ID is equal to IDSS into 1 minus VGS upon VP the whole square. So what we want? We want GM, right? And what is GM given by? GM is given by delta ID upon delta VGS. So we have to differentiate the above expression with respect to delta VGS. Okay, so what do we get if we differentiate the above expression? Okay, so you'll get twice IDSS, and minus 1 upon VP will be outside. It's a constant, right? Into 1 minus VGS upon VP. Okay, everyone agrees to this? Differentiation, we are differentiating this equation with respect to VGS. So you will have twice IDSS into minus 1 upon VP. Why minus 1 upon VP? Because it is associated with VGS into 1 minus VGS upon VP. Okay, and we further write it down as GM is equal to VP itself is negative. You know, VP itself is negative. So we write it over here twice IDSS upon VP into 1 minus VGS upon VP. So we write a mod over here just for simplicity. So this is the expression, and this is the derivation of GM, that is transconductance. And this formula will be very helpful while you solve a numerical on a JFET amplifier. I guess you must have seen this GM before. So this GM, I am writing it, rewriting it in the form GM is equal to GMO times 1 minus VGS upon VP, where GMO is nothing but your GMO is nothing but twice IDSS upon mod of VP. Okay, it is very, very clear. So kindly note down this equation, it will come in very handy. GM is equal to twice IDSS upon mod of VP into 1 minus VGS upon VP. Fine with this? Are we ready?
Yes, sir.
Okay. So let's signal model for a JFET. Okay. So this is my, and what is this small signal model? This small signal model represents only time varying quantities. Remember that. What is this? In short, what is this? Small signal model of a JFET is an attempt to make a non-linear JFET into a linear JFET. Okay, and I have told you already the significance of small signal. What is small signal? I have already discussed that. Now, this is the symbol of a JFET: gate, drain, and source. So I have denoted it as a gate, drain, and source. Source I have connected at the bottom, is reverse bias. What happens due to that? Your gate current is zero. And how do you represent? Am I audible, students?
Yeah,
Hello.
sir.
Yes, sir.
Yes, okay. Yeah. Okay. Thank you. So if I want to represent something current as zero, I can represent it by a open circuit only. Correct? If I want to represent something as a current as a zero, so I am writing over here my gate current IG is zero. That means no current flows into the terminals of your JFET. Yes, and that is represented by a open circuit over here. We don't have anything connected between your gate and source terminal. We have just a voltage VGS. It's open circuit. Okay. Now, what is connected between drain and source? You remember in a JFET, your current starts flowing in which direction? It flows from drain to source, represented by ID. Okay, so between your drain and source current flows. Okay, we cannot show over here the current as a DC current, we have to show the change. So we have written something before. We have written over here delta id. Delta id is written as gm into delta vgs. Correct? That is what we have written. So we will draw a current source between drain and source of a value gm into delta vgs. Okay, so we'll have over here between drain and source, we have a voltage dependent current source. Okay, whose value is how much? GM into delta VGS. Now instead of writing delta VGS, we will use a small signal quantity, right? So now we will, from now on, we will write it as, oh sorry, we will write it as this quantity as GM into small VGS. So this small VGS represents the changes. It represents the delta VGS only. Okay. So what is this GM into VGS represents? It represents the change in ID. And how is that? We already know delta ID is given by GM times delta VGS. GM times delta VGS. Okay. And that is what is representing. So this is your current only, right? This is nothing but your current only. So that is how we represent the first version of your small signal model. Okay, so this gm into vgs represents the small fluctuations in the current id. Okay, so that remember that exponential curve, that straight line we have drawn a linear segment. Why this is so? Because if you follow this, then only your amplifier will be a linear amplifier. Linear amplifier meaning if you apply a small sine wave, output will be a bigger sine wave. If it is not linear, If you apply a small sine wave, output may not be a bigger sine wave at all. It will be different wave step only. I hope this is clear. Up till here, any doubt, anyone? So please draw this small signal model of a JFET. I'm sure you must have already seen this before. But after today's few minutes together, I hope that you all have little bit understood more about it. Why we draw this and what is the signal model of a JFET. In front of you is the proof of it. So this will make sure that your JFET as a device will work as a linear element, and hence your your amplifier JFET as an amplifier work as a linear amplifier. Any doubts so far? Yes.
Yeah. So this diagram is also called as hybrid, right?
Yeah, it is also called as hybrid pi model. Yeah, I will tell you that also. See, pi hota hai na pi. How you
Yeah.
represent a pi symbol? बराबर है?
Yeah, sir.
You represent this pi symbol like this,
Yeah.
na? And why it is called as hybrid? Hybrid क्यों बोलते हैं? Because of the the unit, the parameters के unit. See, the GM का unit is milliampere per volt. Then you have one more resistance which is coming up. Okay, and we have a VGS which is a voltage. So because of the hybrid parameters, this is also in general small signal model of a JFET. Fine. You all
Yes,
have
sir.
drawn this. Can we move forward?
Yes, sir.
Okay, fine.
Yes, sir.
Yeah. Okay, fine. So I hope that you have understood why this gate to source terminal is, why the gate to source terminal is open circuit, and why there is a current source. Why there is a voltage dependent current source. Why we call it a diamond structure means it's a voltage dependent. Matlab the value of ID is dependent upon VGS. And what is VGS? VGS is the input side. That is why something else is controlling this current source. And that something else is VGS, which is not here, which is at the input side, VGS, gate and source terminal. Okay. So the small signal model represents only the, remember, small signal model or whatever, I mean, you want to call it as a hybrid pi model, it represents only the changes in voltage and the current parameters. That is small VGS and small ID. And this small signal model suggests that your drain fluctuations, the drain current fluctuations is equal to the VGS fluctuations times the slope, slope, that is GM. So what are we saying is this only, na? Your drain current fluctuations is equal to the gate to source fluctuations times the slope, and this GM is almost almost a constant value. That's what we are relating. तुम लोग देखो, if you remember carefully, what was the original formula for ID and VGS? ID is IDSS 1 minus VGS upon VP the whole square. वो non-linear हो गया ना? Now you see the relation between current and the voltage. GM is a constant, we are saying. So linear हो गया कि नहीं? This relation is a linear relation. Simple. So that is what we are trying to achieve over here. Okay, we are making the JFET, attempt to make the JFET as a linear element, a linear device. Now और एक term है, and then we are done with the entire small signal model. So this I have already talked before. So if you see the output characteristics of a JFET, we saw that in the saturation region the current is almost a constant, but reality में constant होता नहीं है. Okay, so this region over here, let me mark this region. Okay, so ये जो region है ना, this is saturation region. Okay, this region is saturation region. So in this saturation region your current is supposed to be a constant value, but it is never a constant, it is slightly increasing. So इसका जो slope होगा ना, the slope of this line in the saturation region, 1 upon slope is, we call it as a RO. Okay, 1 upon slope we'll call it as a RO. What is will be the slope? Y2 minus y1 upon x2 minus x1. and that will be delta ID upon delta VDS. So RO will be 1 upon slope, which will be delta VDS upon delta ID. मतलब current voltage divided by current मतलब resistance हो गया, right? So this RO is called as small signal output resistance of a JFET biased in the saturation region. This yellow color region, as I've already told you, is the region where is the saturation region for the MOSFET. Okay, is the saturation region for the MOSFET. So this is again a small signal output resistance. Okay, a small signal output resistance where delta VDS and delta ID also again represents the small changes in ID and small changes in VDS. You remember earlier we started a lecture with this small changes in ID. This is what you mean by um, this diagram which you see over here, small changes in ID. Fine. Now let me get back to the topic. So हमें क्या करना है next? Next we have to derive this RO formula. Okay. It is also called as RO or RD. It is also called as small RO or small RD. Okay. Now let us concentrate on that. Now ये जो equation which you see in front of you right now, this equation which you see in front of you right now, ID is equal to IDSS 1 minus VGS upon VP the whole square. You will say, sir, why there is a term 1 plus lambda VDS? See, this equation, let me show it to you. This equation supports this graph. Okay, and this additional term will represent for this change. Are you understanding? This is your VDS versus ID graph. The purple color, the equation represents that it predicts that the current is a straight line. I mean, it's a constant, independent of VDS. But this pink color line means that the ID is increasing with increasing VDS value, and that is accounted for by this expression, where lambda is the channeling modulation parameter. We will discuss that. It is not so much of concern over here. Right now, you just concentrate on this. Okay. So what is the RD ka form? I mean, what is the RD definition? RD definition is, let me reduce the, so you can write along. RD is given by RD expression is given by delta VDS upon delta ID. Okay, but with the help of this expression, first we will determine delta ID upon delta VDS. Okay, so first let us find delta ID divided by delta VDS. मतलब the above expression we are differentiating with respect to VDS. मतलब ये IDSS into 1 minus VGS upon VP the whole square, ये पूरा का पूरा constant हो गया. Correct? So I will write over here delta ID upon delta VDS, which is the differentiation of this, will be, what will the differentiation? It will be lambda times IDSS into 1 minus VGS upon VP the whole square. Just look at the derivation. Okay, delta ID upon delta VDS is lambda times 1 minus VGS upon VP the whole square into IDSS. Okay, everyone agree to this?
Yes, sir.
But ये जो है expression, this expression is change in ID upon change in VDS, and I can substitute this value. ये जो equation है, I can substitute this value as ID itself, right? ये तो ID क्यों ही है ना? So I can write this as lambda IDQ itself. But हमें क्या चाहिए? हमें RD चाहिए ना? So what will be RD? RD will be 1 upon this, na? 1 upon this, because RD will be delta VDS upon ID, na? So it will be, the answer will be small RD or RO will be 1 divided by lambda into IDQ, which is this formula. Okay, so this is your small signal output resistance. Okay, and this resistance occurs between the drain and the source terminal. Okay, here lambda is I want to write it once. It accounts for that increase in the current. So this is the channel length modulation parameter. Don't bother about it much. You will be studying this in detail a little later. Right now, I don't want to explore that. So where it is lambda, RD formula is 1 divided by lambda into IQ. Do we have? We have nothing. We have just voltage VGS. ऐसे ही connect करना है VGS. Between drain and source, what do we have? We have a current source with a value GM. Oh, let me write a little small. With a value GM into VGS. And what else have to be connected now? This RD, this RD also have to be accounted for. So this RD will represent, this is RD. So this RD will represent the output resistance between the drain and the source terminal. अगर RD और RO नहीं connect किया, if you don't connect this RD, what will happen? It means that you have a ideal source. That means if you don't connect RD, you will get a graph which is like this purple color. And if you include RD, it will like a pink color. It will slightly increase. The current will slightly increase. And this is the complete small signal model for a JFET. Okay. This is the complete small signal model for a JFET. Everyone understanding?
Yes,
Yes,
sir.
sir.
Okay, now with this background story, we can begin with JFET amplifier. Okay, don't worry, we are going very slow because this is a very vital topic. This is exactly same for MOSFET also. If you understand this properly, you will also understand your मैंने बोला था ना starting में, the AC analysis of JFET and MOSFET are same. The AC analysis of JFET and MOSFET are same. Okay, now let us start building. You all can also write it along with me. Let us start building your JFET amplifier. Okay, so let me go over here and let me write over here at the topic as JFET amplifier. इसके तीन प्रकार है depending upon the configuration. Common gate. You can have three types of JFET amplifiers. You have common gate, then you have common drain, and then you have common source. Common gate, common drain, common source. In the interest of time, we are only going to discuss common source amplifier. Let's draw this once. Common source. JFET as a common source amplifier we are going to study now. Okay. So पहले तो everyone draw the self biasing circuit of a JFET. पहले क्या करना है? पहले बनाना है self biasing circuit of a JFET. तो self biasing circuit कैसे दिखता है? You first draw the JFET. Okay. So you first draw the JFET. Mark कर लो terminals, gate, drain and source. Easy. Then जो biasing registers है ना वो बनाने next. So तीनों टर्मिनल में 1 1 रजिस्टर यू हैव टू कनेक्ट. So and how will you name it? You will name it as R RD. This is RG and this is RS. Okay. So ये मेरा बन गया biasing self biasing circuit. But self biasing circuit, if you say, you will also require a DC voltage source, a DC voltage source. ये जो ऊपर लिखा है ना VDD is provided DC voltage source. And okay, yeah. So I think everyone has drawn this cell biasing circuit, okay, for a JFET, and now we are going to make it as an amplifier. तो amplifier के लिए क्या क्या चाहिए? We are going to use a different color, only red color for the amplifier. So amplifier के लिए I've told you we have to superimpose AC भी चाहिए ना? So AC also we have to give. So let me give a voltage source. Now voltage source को कैसे represent करोगे? this is my, oh, sorry, this is my voltage source. Ideal voltage source nahi hai, it is a finite voltage source. So practical voltage source will have a series internal resistance. We call it as a R sig. So ये R sig is the internal resistance of this voltage source. Okay, and मेरा output कहाँ पे connect करोगे? Where I will connect the output? Output I will connect it from the drain terminal. Okay, I will also tell you why this is called as a common source amplifier. Acha, I have to connect my AC. I have to connect my AC, but can I connect my AC directly to this? So what I mean to say is, do I connect this directly to the gate? Yes or no? Or is there a solution to it? Or will that be a problem? What should I do? Should I directly connect the, you know, this source to the gate terminal? No, I cannot do that. I have to connect
Capacitor.
a capacitor.
Capacitor
Yes,
coupling.
yes. This is called as input coupling capacitor CC1. Now ये करता क्या है input coupling capacitor? Input coupling capacitor blocks DC. So तुम्हारा जो AC signal जा रहा है, it will be safe reaching the gate terminal. अगर if you don't connect your coupling capacitor, input coupling capacitor, what will happen? Your AC and DC will be overridden with each other. So जो AC है that will influence your DC. And तुम्हें क्या चाहिए? तुम्हारा Q point should not disturb. Your AC signal should not disturb the Q point. That's why we are connecting a input coupling capacitor CC1. Okay. Also, you connect your bypass capacitor similarly over here, which is CS. Role of the bypass capacitor is again the same. It will bypass any AC to the ground. And at the output also, over here, we connect it. This we call it CC2 or CO, whatever its name is the literature. And ये मेरा हो गया output. Now output में what you can connect? Output में you can connect a load. Okay? Output में you can connect a load. Here is my load. This is my load, RL. This is my RL load. And finally, I will mark the output. So this is my output. Okay, so I have my RL as a load. So in short, मेरा amplifier किधर है? Where is my amplifier? So basically, I am marking something over here. This part, ये जो yellow color region बना है, this is my amplifier. तो ये मेरा ये left hand side क्या है? I mean, sorry, I am not included the capacitor. This capacitor also should be included. This is my amplifier. So what is that side on the left hand side? ये मेरा source हो गया. This is my source. Okay, this is my source. This yellow color region over here is my amplifier. This yellow color region over here is my amplifier. And what is this? This RL, that is the load. This is the load. मतलब amplifier, what do you connect to the amplifier? You connect a source to the amplifier, correct? And amplifier किसको connect करते हैं? Amplifier you connect it to something, right? And that is called as a load. Okay, so this becomes my common source amplifier. So why it is called as the common source? Common source इसको क्यों बोलते हैं? Because the reason being your input जो है ना, that is applied to the gate terminal. So your input is applied to the gate. So whenever we have an input applied to the gate and your output, ये जो output है ना, output is sensed at the drain. Output is measured or sensed at the drain terminal, then it is called as a common source amplifier. Okay, so I repeat, my Vin and RSIC forms the source. This is my JFET biasing circuit with along with the 3 coupling capacitors. CC1 and CC2 are called as the coupling capacitors, and CS is called as the bypass capacitor. Okay, and RL is the load. And why it is called as common source? Because input is applied to the gate terminal and output is sensed at the drain terminal. Okay, many of y'all also think it is called as a common source because source is common between input and output. Correct? ऐसे भी सुना रहेगा ना? Source is common between input and output. That is why it is called as a
Yes,
common
sir.
source. But in looking, but that is not true looking at this diagram. That is true looking at the AC equivalent circuit. वो AC equivalent circuit में we can say that, not in this. Okay, not in this diagram we can say that because इधर source किधर common दिख रहा है ना? We have a RS also connected. Okay, so that will be visibly clear when you do the AC equivalent. इसका भी क्या करने का next? What is the next step? You draw the small signal equivalent of your JFET and then you connect all the external components which you want to connect. उसका analysis करो and you determine its voltage gain, you determine its input impedance and you determine its output impedance of the circuit. And बन गया मेरा amplifier. You simulated it anti-spice, मेरा amplifier बन गया. Okay, so right now I am not continuing further. What I will do instead is I will tell you what is my plan. So देखो, last time we have solved a numerical. ये दिखा है ना numerical. So what I will do, I will prepare a very short video of let's say 5 to 10 minutes, which will explain to you how to solve a JFET amplifier numerical. Okay, so what I will use is I will use all the values from here. मैं ऐसे ही बता दूंगा कि ये सब values हम लोग ने solve कर चुके हैं and I will build up from here कि इसके आगे क्या करना है. Is this fine? Then I will not derive the formula for AV and voltage gain and output and input impedance, but I'll directly use them. Okay, so you will learn the technique कि if I am given an amplifier circuit, how to determine, because amplifier के लिए क्या क्या important है? Amplifier के लिए you have to determine the voltage gain, you have to determine the Zn, you have to determine the output impedance. Abhi you might be knowing it. All of you for all the circuits, whatever you have studied in ECAD, यही करते आ रहे हो, correct? Voltage gain, Zn and Z out. Nothing new in this, correct ना? For all the
Yes,
circuits,
sir.
you are doing the same thing. Voltage gain, Zn निकालो, Z out निकालो. That's it. Why क्यों निकालना है? कौन पूछेगा? Why we are doing it? Because it is mandatory. करना ही है. So amplifier के लिए. So next time, whenever you determine, you can ask your teacher also. Why we are determining only voltage gain? Cannot be determined current gain? Cannot be determined something? I mean, there are 4 varieties of amplifiers, right? You're studying only 2. I mean, only one in fact. Current gain to you are determining for some other configuration if it is required. Anyways, I'll stop over here. And in that short video, I will explain it to you numerically how to solve this how to solve this, how to attempt a common source amplifier numerical. Okay, so please wait for 1 minute.